Okay, so this is gonna be part two, I suppose, right? Uh, let's see if maybe you just watched the last video, hopefully, or if it's been like 2 days, then let's see, right? So we talked about basically the negation of a statement just needs to be the opposite of the original statement, right? We talked about and, this is how it goes, or this is how it goes, and if P then Q, this is how it goes, right? Now there's a P implies Q, right? But it's not always the case that just because if P then Q is a statement, just because P implies Q doesn't have to mean that Q implies P, right? So I mean, like I said, the statement says that if you add two even numbers, then their sum is even. What would the statement if Q then P would be? I guess you can translate it as if the sum of two, let's just to keep it simple, let's talk about natural numbers, right? Suppose the statement Q then P would have to mean something like if the sum if the sum of two natural numbers is even, then both the numbers were even to begin with, So say if n plus m is even, and let's just already say that n and m, we just know that they're already natural numbers, right? So I guess this kind of a disclaimer. So if n plus m is even, and we know that they're natural numbers, then both n and m were even to begin with. I think that's kind of how you would say the statement if Q then P would be, something like that. But this statement doesn't have to be true. So the statement if P then Q of if you add two even numbers, then their sum is even. I promised you we'll look at it. We'll look at it in the future. But for now, just trust me that it's definitely a true statement. However, the statement of if the addition of two natural numbers is even, then both of the numbers were even to begin with, that is not a true statement, because I think we said it over here, right? 3 plus 5, right? 3 plus 5 is definitely even. 3 plus 5 is even. But neither actually, this actually fails for both the letters, or both the numbers. 3, even though the 3 plus 5 is even, because it's 8, neither 3 nor 5 is even, right? So just because if P then Q is true, does not have to mean that if Q then P is true. However, when you find a statement for which P implies Q and Q implies P, that's when you find out an if and only if statement. So that's basically what we want. And if we want an if and only if statement to be the case in which both if P then Q is false is true, and also if Q then P is true. Let me put that in a truth table so that it makes more sense, right? So we want let me just write this, right? We want the statement. We want the statement P if and only if Q to mean to be equal to the statement P implies Q and Q implies P. So that's what we want the if and only if to mean. We want if P, if and so again, that's why the arrow goes both ways. P implies Q, but also Q implies P. So we want P if and only if Q to be the equivalent of P implies Q and Q implies P. Notice how I wrote and this way, right? So we're gonna do truth tables. So right now we're only dealing with a P and Q. If for some reason we did P and Q and R, then we would have to do all cases of three statements. So for one statement, there's only two cases, it's either true or false. For two statements, there's four cases, right? So if we had P, Q, and another letter R, we would need 8 cases. I'll let you think about that one. But okay, right now we only have P and Q's. So if I make a truth table, so again, there's only 4 possibilities that these guys go. True, 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 false, false, true, false, false, right? Okay, we wanna look what the truth table for this looks like. So in order for us to look at that, we need to first figure out what the truth table is for if P then Q. Well, we did that in the last video, right? So true, false, true, true. Okay, well, right beside us, we're gonna do if Q then P, and again the same rules apply, meaning if Q is true and P is true, then this statement is true. So case 1, they're both true, so then Q is true and P is true. So in this situation, we actually gotta read from right to left. That would be like a easy way of doing it, right? So true, true means that this is true. Okay, if Q is false but P is true, well, what did we say? If this thing is false, if Q alone is false, then the if P then Q statement itself will be true. So if Q is false and P is true, then this is still true. Okay, if Q is true but P is false, and we're looking at if Q then P. If this is true but this is false, okay, that's when this is false. And if this is false and this is false, well, we said that this should be true because you're saying that Q is false, so the if Q then P is true. Again, you have a problem, take it up with the previous video. Leave a comment over there. But now we have the statement P implies Q. These are the truth tables for the statement P implies Q. We want to know the values for this and Q implies P. So basically, what we did over here, so again, the statement P and Q, or just A and B, is true when they're both true, but then false if at least one of them is false. Okay, so let's go back here, right? This is this and that. It's this and that. So that's what I'm saying. Think of this as maybe A and this is B, and this is really A and B, right? So we're looking at these truth tables and we're gonna see the values that go here from these two. All right. So if A is true and B is true, then A and B is true. Okay. A is true, but A is false, but B is true. Oh, at least one of them was false, right? So then this is false. A is true, but B is false. Okay, so then this statement has to be false. And then this is true, and this is true, so this is true. So this is what the statement P and Q and Q and P looks like, right? What does this mean, right? Well, we're saying that we want this basically to be the same thing as P if and only if Q, right? True, false, false, true. So then let's look at the original P and Q, right? I don't know if I really need to use colors, but so let's focus on these ones, right? So we're saying that the statement P if and only if Q, if both of them are true, then P if and only if Q is true. If one's true but the other's false, then the statement is false. But then, if both of them are false, the statement P if and only if Q is true, right? So how can we summarize what we just found out? Basically, we summarize that the statement P if and only if Q. Wow, I thought I had more ink on this one. The statement, you can barely even see it. The statement P, let me use something else. So P if and only if Q is, what are we trying to say? We're trying to say that this statement P if and only if Q is true when both P and Q are true, or when both P and Q are false. I mean, what does P if and only if Q mean, right? We're saying that, okay, if P is true, then Q has to be true. And then if P is false, then Q has to be false. That's kind of like the takeaway, right? The statement P if and only if Q is true when both of them are true, or it's true when both of them are false. And therefore, by leftovers, or whatever you want to call it, that the statement P if and only if Q is going to be false, well, if they don't match, basically. So again, the statement P if and only if Q is true when they're either both true or both false. So what can we how can we use this fact, right? Okay, well, let me show you a few. I wonder if we have time. Yeah, I think we have time. Right. I want to prove this following thing, and I'm basically going to prove it with just truth tables. There might be some really long truth tables, but they're going to be whatever, right? So I want to prove this statement. Let's say prove. The negation of P and Q is equivalent to, meaning this statement if and only if, this other statement, not P or not Q. So I'm saying that this statement here alone, the negation of P and Q, is equivalent, meaning if this is if and only if, this other statement, not P or not Q. I don't know. You before while I write down these truth tables, right? You can think about it yourself, right? So if you know, think of a statement that's P and Q. So like, I don't know. Again, blue car. So someone tells you can only get a blue car, right? So then the negation is you have to get something that's not a blue car. Well, according to this thing, then you can get something that's either not blue or get something that's not a car, right? The negation of something that's blue and a car is something that's not blue or something that's not a car. I don't know. Let it sink in your mind. But apparently I'm going to prove it, so it must be true, right? Spoiler alert. Okay, P, Q. Same old, true, true, false, false, true, false, false. Okay, what truth table should I do in order to prove this statement, right? Well, I'm gonna need this one, and then I'm gonna need this one, right? Um, so P and Q, right? The only way I'm gonna have a truth table values for the statement not P and Q is that I need to know P and Q first, which we already know true is true, but then false every other case, right? If this is statement P and Q, then the negation of P and Q needs to be that the values are opposite, right? So if this is true, then this is false. And if these ones are false, then these ones have to be true. Okay. Now, what do I need to know for this statement? This or that? Well, I need to know what not P is what are the values for not P. And then I need to know what are the values for not Q. And once I know the values for not P and not Q, then I can look at not P or not Q. See how that goes? Probably not, because it's all the way over there, right? So, okay, not P, right? So not P is just the negation of P, right? So true, true, false, false. There needs to be false, false, true, true. And then this is the negation of Q. So true, false, and this should be false, true, false, true. Okay, and then now this is my A and that's my B, and I'm thinking A or B. So and again or, right? Or. So if this is false and that's false, then this has to be false. But for the or, you only need at least one of them to be true, right? So false, but this one's true, so then it's true. True, but this one's false. Okay, this one's true, then it's true. And over here they're both true, so then it's true. Okay, now I think we have all that we need, really. So here's why I was making a whole big deal about this little sentence, right? Is because now I'm just gonna look at the statement directly. I'm gonna look at this statement, not P or Q, if and only if not P or not Q. Right? So again, let me use a color. This is like my A and my B. Okay, my A's are here, all the way over here. That's the truth table for not P and Q, and the truth table for not P or not Q is this one. So this is my A and that's my B. So what did we say about if and only if statements? So the if and only if statement is only true when they're either both true or both false. When they're either both true or both false, right? So if A is false and B is false, then this thing is true, right? Because if A was false and B was false, then A, if and only if B, needs to be true. This is true and that's true, then that's true. This is true and that's true, then that's true. And this is true and that's true, then that's true. Okay. So what happened here? What did we end up proving? What we prove is the following. I should have said this a long time ago, and sadly I don't have space anywhere to write this. So I'll just make space over here. It's gonna come out blurry, but whatever. A tautology, Tautology, I think that's how you spell it. A tautology is a statement that is always true. Wow. So by the way, I'll write it here too. A contradiction is a statement that is always false. That always false. So why am I introducing this vocabulary? Notice that the statement this, if and only if that, the truth table came out to be true every single time. When you get a statement for which all you have is true the entire time, we call that a tautology. Okay. More than that, we're saying that the statement not P and Q, if and only if, not P or not Q, we're saying that this statement is always true. Apparently so. No matter what, Again, we see that P could be true and false, Q could be true and false independently of each other, and yet we figured out a sentence or a statement that always is true, never fails to be true. Similarly, we're saying that the statement A right here and the statement B right here, that they're logically equivalent. That's what if and only if means too. But yeah, so we've proven that the statement not P and Q is equivalent to the statement not P or not Q. This is one of it goes by the name of the Morgan's law, I think. I mean, at least this is one of them. There's a second, the Morgan's law, which I think we have time for. I'll do it. But yeah, so this is how we prove that two statements are. This is one way to prove that two statements are equivalent, meaning that this statement right here is equivalent to that statement. So, again, I don't know. I told you guys to try to rack your brains around it, but I just proved it to be true. How do you feel about this proof, right? Like, is it lame, or like, do you not like that we're proving things with logic? I don't know who wouldn't like that. Well, anyways, right? So the funny thing is to say. So again, the funny thing was that the negation of P and Q is not P or not Q, right? So then now we're gonna do the opposite. We're gonna prove the negation of P or Q is equivalent to not P and not Q. So this statement, again, you can say that's a sentence, right? Maybe, I don't know, blue car. Someone tells you pick something that's not blue or a car. So you gotta pick something that's not blue or a car. Well, apparently so. The statement of picking something that's not blue or a car is equivalent to the statement pick something that's not blue and also not a car. Again, I'll let your brain, I'll let you guys think about that, right? Let me do this real fast because I already did the other one. So P and Q. True, false, false. True, false, right? What am I going to need? P or Q? I need P or Q. So once I figure that out, then I'm going to have the statement not P or Q. And then on the other side, I'm going to need a not P and I'm going to need a not Q. And then I'm going to have to look at not P and not Q. Alright, so or only one of them has to be true, so true, false. So then now this is false, true. And then now P is going to be false, false, true, true. So now Q is false, true, false, true. Okay, now I'm saying and for these two. So and means that they both have to be true. False, false, then false. False, true, then false. True, false, then false. True, true is true. And then now, so not P or Q, equivalent to not P and not Q. This is my A, and this is my B. So this is my B right here. This is my A. So again, we're doing if and only if, right? So again, if they match, then it's true. If they don't match, it's false, right? So false, false, then this is true. False, false, then it's true. False, false, then it's true. True, true, then it's true. So again, that's the second, the Morgan's law. Okay. Yeah. Let me know how you guys are feeling. Also, let me know if you guys like these shorter videos. I mean, not that short, right? I'm going down from 55 minutes to 50 to 45. Right now, this one's gonna be a little bit less than 30. Yeah, just give me with some feedback. Do you guys get it? Do you guys not get it? Do you guys have a problem? Do these math majors have too much power, saying that this is true and this is not true with this silly truth tables? I mean, let me know. That being said, one thing you can tell whether it's gonna be a tautology, the A if and only if B. Well, basically their truth tables gotta match, right? FFFT, FFFT, right? And if I go back, I'm pretty sure the other one matched exactly, right? I mean, better. I mean, if it ended up being a tautology, better, right? Again, this was my A, F, T, T, T. This was my B, F, T, 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 right? So again, someone might even say, you don't really need to do this step if you can already tell that they're gonna be the exact same team. Now, by the way, look at how these two, even though they match with each other, they don't really match with all the other ones, right? So it's not just, so you might think, oh, it's just a coincidence, man. It's just a coincidence. I don't know. It doesn't look like they're matching on the others spots, right? I mean, again, one time you're gonna definitely have a coincidence if you come up with tautologies, right? So a tautology is a statement that's always true. I mean, you can, I'll give you guys a real quick tautology. So you have basically this one, right? My tautology right here is that either A or not A. How about that one? Right? Like no matter what your statement A is, as long as it's a statement, as long as it's either true or false, right? So as long as it's either true or false, then this is going to be false true. So if I tell you either A or not A, well, this is true and this is true. So hey, I ended up with a tautology, right? Not an impressive tautology because, yeah, I mean, I'm just saying something either is or it isn't. So for next video, I'm gonna show you. I don't know if I'll prove them, but I'll show you tautologies. But also, I don't know. Let's see if you can come up with with some tautologies of your own before next video hits. Can you create a statement that's always true, like I just did? Even though this one's kind of lame, right? A or not A. I mean, duh. But hey, I don't know. You come up with another one. See if you're that cool. All right. So leave a like and drop a comment. Even if you don't come up with a tautology, just let me know. Any questions you may have, and I'll see you on the next one.